So here, see here the relationship between your variable, versus the target. You can see there is not a straight line, but a kind of curve. So if you try to fit a line, so it won't be a proper. Uh, so what you do is you go for polynomial regression. Under the hood, it uses the linear regression model, but uh, instead it uses the polynomial function. So for degree 3, and here when degree 15 is there, you can see that although it is fitting all the data point, but this is called as overfitting. So there are concept of underfitting when your model is not whatever the line or hyperplane, whatever it is not fitting in the data points properly. So you need to increase the degree. That is, you have to go for polynomial regression. So in that case, you have to be very cautious that the you don't go and do the higher degree and do the overfitting. So underfitting and overfitting will give a bad result for the future data set. Overfitting might will sound like a kind of good model, but when you test it or when you predict for the future price, it will have a very bad output. So degree, you have to be very, you have to be find the sweet spot. So let's see. So let's see. So same thing can be. In our earlier case, we use the linear regression, but let's see there are another type of algorithm which can solve this problem of finding the y, that is price. So there is a kind of algorithm called decision tree. So decision tree works by asking a series of yes/no questions to split the data. So you can think it in terms of like 20 questions. If the house is bigger than 15,000 square feet, then yes. Is it Mumbai? If yes, then predict price 1.2 crore. So it keeps on asking question yes or no, and it tries to, based on the data, it tries to split the, find the uh, this pattern on its own. So here, if square feet is greater than 1500, then yes. Then bedroom greater than 2, then yes or no. It so basically this is something which we don't which the model in itself build this decision tree. This is something not we define it. We provide the data, we provide the what the variables are, and based on the all the data point, it tries to keep on splitting the data and comes a decision tree like this. So in a way, uh, you can say that rather than hard coding the logic, it finds the pattern in the data and find the if and else condition in it. So here, let's use the linear decision tree. So for that, we will use sklearn tree, decision tree regressor, and here the process is same. Decision tree regressor, maximum depth. So basically, how much uh, decision level it has to go under. So basically here, we can ask the, we can limit the depth of this branch of the model. So here, since we can, in this case, variable is only 3 variables are there. We can keep max depth as 4. Random state. So initially, how the decision process, splitting the data should start. We can randomize it and set the state as 42, and then we can call fit. The method is same like how we did for our linear regression model.fit. So here also decision tree instance dot fit, and we are passing x train and y train, and then the model is trained, and then we can pass the x test and then get the y prediction, and then evaluation is going to be same here, R2 score and mean squared error. So, and then let's see. So here you can see that tree R2 score. Here you can compare then the model quality. Here it's 0.98 and here it's 0.92. Decision tree RMSE 10 lakh, around 10 lakh, and here it's around 4 lakh. So here our root mean, according to the root mean square error, the error is higher. So this model is not necessarily a good fit, but this can be a so basically since we have synthetic data, but in, let's say if you have real data, the situation might be different, and this model can be a good fit and can turn out that RMSE is low. We never know. So it totally depends on the kind of data what we have and kind of problem we are trying to tackle. So, and now here one more thing we can do is we can visualize the tree what it has built. So here what we are going to do is we are going to use the plot tree method, which is provided by the sklearn tree package plot tree, and it internally it uses matplotlib to plot the decision tree. And here we are passing the model and the columns, we that is what are the variables, and then here we are setting the title, and just we are asking it to show the decision tree. And here again we are adding uh, data points that this is another chart. This will show another chart which shows which feature importance was given in the decision tree. So here when we train the decision tree, it creates a variable inside that feature importance. What feature importance it found that are important, and then we are extracting those value, and then we are sorting its value, and then we are plotting it uh, as a horizontal bar graph. So we are going to see two graph over here. One is the decision tree plot itself, the how the decision tree looks like. So here you can see that how it determined. So here, if square feet is less than this, then true or false. Then again, it created a filter. If square feet is less than this or uh, this, then yes or no. And then here you can see that in the false branch, you can see again it is trying to filter the data based on the square feet. And if bedroom is less than 2.5, and so you can see that it kept on splitting the data. And based on this, this is the class it identifies as the output. So here, based on the data, it try to find the pattern in it, and based on the flow, it at the end it reaches the its printed price. And then we have the other graph which shows the importance. So definitely from here we can see that the square feet is the main variable. It is giving the most importance, and you can see here also that the feature importance, uh, it is giving more than you can say around more than 95 90 around 95% is giving importance to square feet, then bedroom, and then age year. So it determines that the square feet is of more importance than bedroom and age year for determining the price. So linear regression, the decision tree, and then we have random forest regressor. So random forest or ensemble learning. So when we have, so exactly a random forest is a collection of many, you can say a collection of many decision tree that work together. So many decision tree, and each tree sees a random subset of data and feature, then they all vote on the prediction. So in a way, you can say that multiple data cluster is found out, and based on that multiple trees are constructed, and each tree then vote on the prediction. The average of many imperfect trees, then the average is taken, and then definitely its output will be better than the perfect tree. So random forest gives in a way a better prediction for a complex data set, um, and complex data set. If we just build just simple plain old decision tree, random forest much more accurate, because we are building multiple decision trees based on the cluster of data set. And this type of machine learning is also called as ensemble learning. Why? Because here we are combining weak learner to create a strong learner, and it is just not limited to uh, our decision tree, but any kind of ML algorithm, which is collection of multiple algorithm, which whose goal is to combine the weak learner to create a strong learner. So random forest is often the first algorithm data science try, because it's more accurate, handles non-linearity, requires minimal pre-processing, and it rarely overfits. So this random forest is very, very widely used and very uh, uh, trusted algorithm for supervised machine learning. So let's see how to go about it. So first we import from ensemble, we import random forest regressor, and then the steps are same. We train, we first we create the random forest regressor. Here, n estimator, number of trees, more equal to better but slower. So you can initially start with less number, see how the model is performing, and then if you see that if efficiency can be increased uh, by increasing the number of estimator, then you can go ahead. Maximum depth of each tree. So all these things are, you need to fine tune it. You need to see after the evaluation, you can go ahead and again fine tune the estimator max depth and minimum sample split to see how the evaluation of the model is behaving. And after that, you fit the model and then you predict, and then you see R2 score and mean squared error. So that's the whole step. So here you can see that random forest RMSE is 689 6 lakh 89. And if you have looked at, if you look compare it with the decision tree, definitely it is much better. And also if you compare it with the linear regression, it is also much better. So for linear regression it was 417, and for in this case it is not better than the linear regression, but in most cases it is. Here our data is synthetic, so linear regression is turning out to be a better option, but not necessarily, because most of the real practical case, random forest turns out to be much better. And then again, we can see which feature importance it is giving. Similarly, you can see that square feet is given much more importance. So let's review again our regression matrices. So, so what are the regression matrices? It is a way to know if our model is good. We need matrices, and different matrices highlight different aspects of model performance. So we have already reviewed three. These are the overall standard error matrices in order to determine how the model is behaving. So the goal is you have true value, that is from your data set. In our case, y test. From our previous example, y test, we can call it as y true, that is used to check against the model prediction, and y prediction is the random forest prediction. So here, in order to find the error using the different method, mean absolute error, mean squared error, and the and root mean square error is just the square root of MSE, then R2 score, and then mean absolute percentage error. So these are all different kind of regression matrices. And here, ME stands for mean absolute error. It gives on an average prediction are off by. So here it calculates on an average how much it is off by from the real value. Then we have mean square error. It penalizes large error heavily because it is square. And then root mean square error. Same unit as target, but it is root of this thing, most commonly reported matrices. Then we have R square. So it is percentage of variance explained. So one is perfect. If it is closer to one, in our case, it is most of the model is giving 0.9896. So if it is closer to one, then it is perfect. If it is less than 0.9, in fact, 0.8 is also considered perfect. 0.7 is also sometime, if data is very complex or if you have limited data set, if it is around 0.7, it still can be considered as good. But anything lower than that can be said that it is not that good. And then we have mean absolute percentage error, prediction off by percentage on average. So this thing was in terms of value, and this is in terms of percentage. So here, because uh, here value, in order to know this error, you need to know where your average price is. But if you look at by the percentage, you don't even need to know where your average prices are. Just by looking at the percentage, you can determine that how accurate your model is. Um, so, so So here, on prediction, here, if you see that on average are off by this gives you a raw idea that what is the price difference. But if you look at same thing, if you see it is in terms of percentage, that it is off by on average 5.7%. and this is 0.96. So this is quite good. And here, let me put the formula to how it is calculated. So your so basically here, mean absolute error is calculated by finding the mean of your difference between or the original point and the predicted point. Your mean squared error, you just square the error so that it penalizes large error. So if error is low, then the mean square will be low. But if so, in generally, it gives a large number. If you see the large number, then uh, you can have an idea that the model is not that accurate. So basically, just squares the mean of the difference of the original point and the predicted point, and then RMSE is the square root of MSE. Then R square is your it is the regression is to your total whatever kind of model it was used to train. It tries to plot the actual data point internally for the calculation. You can visualize this thing in a way that it plots the original data point versus the predicted point, and the variance, the how it varies, as we saw that in our earlier case. If I so here so here for example, the this is also not a proper example. Let me show a plot of actual versus. So here, what is the actual price versus what is the actual prices versus the predicted price? So here, in practical scenario, if there is no error, it should lie on the red line. But the further the distance, it means that the error is high, and this variance is what we call R square. So, and you can see the R square formula as is the 1 minus summation of y I, that is your original data point, and y hat I, that is your predicted point, squared divided by your uh, yi and your y bar, and this is how the variance is calculated. And then we have MAPE, which is which is used to calculate the percentage error. So let's quickly compare how the model are different models are behaving. So here, what we'll do, we will quickly use all the different model, linear regression model, decision tree, random forest, SVR, and K neighbor regressor. So here different model we are going to use. So, and now we will then train all the models for the same data set, and then we will see what are its R2 square score. And here you can see that ridge regression, for example, is giving us the most optimal accurate score, R2 score, and lasso regression. So there are different kind of algorithm out there, and so you can see, and this is not a hard and fast rule that in this way our model is going to behave. It totally depends on the data set, what you have, what is the correlationship between the data point variables. So in some cases, linear regression might work better if there is a direct correlation, a linear pattern is there. Random forest might work, or and in most of cases, ridge and lasso might work. So there are different model, and it totally depends on your data and the pattern in the data, which determines which model to use. So, so here, till now, our goal was uh, to regress the data set so that we can find the predict the future price, or not future target value. Not only price, but it totally depends on your data set what you want to determine the target. So these are the class of those subset of algorithm. But now let's say if we want to classify or put uh, a class to particular data point, then in that case we use supervised learning based on classification. So what is classification? Classification predicts a category or class. For example, let's say if you have a e-commerce platform and visitor visit your website. So based on the analytics, the analytics can provide the country of origin, what browser or what operating system or what hardware the user is using, or maybe some analytics can also provide the age group, and different kind of other data also. It can provide the time of the day or different kind of data it can provide, and based on that your model can classify that particular customer as a customer which can be targeted as a kind of you can say a high paying customer, or if you want, if you are doing a credit card transaction, so that particular transaction can be classified as a transaction fraud. So basically when you want to put your data point into a set of predefined category, so that kind of algorithm is called as classification. So in our regression algorithm, we learned linear regression. So linear regression was for finding the future price. And then similar kind of algorithm is there, which is called as logistic regression. Despite its name, regression, but still it is a classification algorithm. So logistic regression is one of the common classification algorithm, and it predicts the probability that an observation belongs to a class. And then it classifies based on a particular threshold. So let's visualize what exactly we are talking about, logistic regression. So logistic regression predicts the probability of belonging to a class. So it under the hood, it uses the same uh, linear regression algorithm, but it classified. So basically, it tries to fit the line, and based on threshold, it tries to classify the data point into two categories. So let's see how to implement the logistic regression. So, from the same linear model, we import logistic regression and data set. For example, here, breast cancer data set we are going to use. And here, let's load the data set and inspect the data set. So here we are loading the cancer data set. We are creating the extracting X based on the column and Y. So basically our goal here is to train the model based on the data set, and if we will see what feature it has, and based on the future feature what we provide, it should classify the particular data point either into malignant or benign. So here we can see that there are 369 rows, samples means rows, and 30 feature. So there are 30 features for each row, and each row is either classified as malign or malignant or benign. So here you can also see that these are the columns inside the data set. The tumors, this is a data related tumor. So mean radius, mean texture, mean perimeter, mean area, mean smoothness, mean. So these are, let's say, data when you do a test on that particular tumor using MRI, using the uh, different intrusive or different kind of method, you get these data point, and the classification was done by the doctor. So now the goal is, if you provide the test report, so without human intervention, it should either classify it into malignant or benign. So so here you have the data set. Now the process is same. First, create the train test plate, and here we are going to use the standard scalar. What does the standard scalar does is, here you can see that each variable has a different uh, range of value. So here mean radius is in 17.99, and if you look at, let's say, mean concave point, it is in terms of 0.14. So what standard scalar does is, it brings on a standard scale for all the variable, and then after that we do the fit transform in for the regression. We only used to call fit, and here fit transform uh, does the scaling, and here yeah, so here also we call the fit transform for one thing only, that is to scale the variable so that it is somewhat the range is same. And then instead of fit, we call transform. Here, okay. So here, these three steps are required when we have a large number of variable and when we want to uh, bring in all the variable in the same range. So proportionality, it adjusts all the variable and brings into the same range proportionately. And then when you're after the transform, when your data is ready, you use this particular output for your classification. So here, in our case, we are going to use logistic regression. So instead of X train, we are going to use X test scaled version, and we'll pass Y train, and then Y train doesn't need scaling. Why? Because it is just class of either malignant or benign tumor. So Y train doesn't need scaling. X train is scaled version, and then we try to fit it. And then after the fitting, here fitting is done for classification purpose. And then in the same way, we are going to call the predict on the test sample. So train, we create train and test, and then we are predicting against it. And then similar way, we can see the accuracy score and classification report. So accuracy is 0.98, and here the classification report precision is around 90. Malignant, it is 98% and 99% accurate. And similarly, we have k nearest neighbor algorithm. So, you can consider k nearest neighbors the most intuitive ML algorithm. It classify a new point. It looks at the k closest neighbor in the training data and let them vote. If let's say 3 out of 5 nearest neighbor, let's say neighbor are cat, then it predict cat. So it sees, so data point, let's say if this is a data point, it sees which are what are the 5 its nearest neighbor point. So here, if you look, these are its nearest neighbor point, and most of the neighbor point are in this in the red category. So in that's how it will classify this into this class. So here we are using iris dataset, same step. Here again we are using the standard scalar. So these are important, these 3 steps are important. Scaling of variable is important if you have a large number of variable, and the range of values in variable are different across all the variable, then you scale it to bring the range same for all the variables. So it adjusts the value proportionately and brings it in the same range. And then you call the you initialize the model. Here we are calling k neighbors classifier with n neighbors equals to 5. So here, let's say if we would have set 5, so it will see what the 5 closest dot, that is data point, and then it, based on the maximum closest data point, that class, then it will predict that class. And the fit method and the predict method. So load iris data set, we need import. So here, now the model after training, the accuracy is around 0.933. So here we also ran range of here, if what we did, what's happening is finding the best k. What we are doing is we are increasing the n neighbor to see how the model performance improve. Here we kept 5 as the default, but we can't be sure that if data points are too much concentrated, then in that case increasing n neighbor might improve the performance. So here what we did, we are increasing range from 2 to 30. So it will try the k-neighbor classifier from 2 to 30 and see how the performance score improves. So, and then we are plotting that thing. So here you can see that after this is the peak, and at the seventh k-neighbor, the model has increased. So you can go for n equals to 7 and or maybe 9, but after that it remains constant and then it falls down. So either you select 7 or 9 to keep your uh, key neighbor classifier as the optimal one. So similarly, we have decision tree classifier. So uh, in our previous case, in the regression model, we used decision tree for regression, but here we can use decision tree for classification also. So same process, decision tree classifier, and then fit, and then the predict, and then its accuracy we are checking, and then the visualization of other decision tree. So here you can see how the decision was made and the classification, how it is generating, and the feature importance. Then there are support vector machine, and then so what we learned right now was classification when we know the output. When we in the case of uh, uh, our cancer data set, we knew that it should be either malignant or benign, and in case of iris, the type of flower it belongs to, the output we already know. But in some cases, and these kind of classes where we know the output in advance, we call that as a supervised learning. And what if we want to discover hidden group in our data set, and when where we don't know the label? So that's what unsupervised learning is all about. And so here we will look at the k-mean clustering. So so basically when you have data point, so uh, and when there is a pattern in the data point, it is forming a group. So in most cases definitely it forms group of data point. For let's say if you consider customers shopping habit, so if you consider all the variable of customer uh, and the amount of shopping the customer has done, you can see, you can classify the customer into different segment. So or so those kind of algorithm where you don't know what kind of pattern exists and you want to find the pattern, in those case clustering algorithm help us, and those kind of algorithm are called as unsupervised learning, because we don't have label, we have to find the discover the group. So here all the data point, let's say in this case, let's keep the scenario simple. We have only feature 1 and feature 2. We plot it, and then we can definitely see that there is a pattern that it can be clustered. And and then this the center of the cluster will define it as the your overall mean of the cluster, and then you can use that to determine the future class of future group the data point will belong to. So here, so you keep the goal is to find the center of the cluster for each group, and then you internally it create a it creates a group, and based on that centroid what the algorithm found, it uses that to determine the future cluster, that what cluster it belongs to. So here we are using make blobs data set. This is used to create a cluster data set. Again we are scaling the data, and here the 3 step: creating the instance of the class, fitting it, and doing the prediction. And then we are visualizing it. So here you can see that this is how our data set looks like. And here it determined the center of the cluster. Here the scenario is simple, that we have only 2 feature, but in practical scenario, a situation can be very complex, that it has n number of feature. So it is not that simple that you can go ahead and uh, visually think that okay, center might be this. In 3D, in 3D space, if 3 variables are there, it will have a depth also. And if it has 4 feature, then it is very hard to determine where it center lies. So K mean cluster is to help us to determine the group of cluster and then find the center of the cluster. So these are the 3 classes of algorithm. This your regression algorithm and the classification algorithm, which are part of your supervised learning, and then the unsupervised learning. For example, k-mean cluster. So these kind of model forms the basics of your all the ML algorithm. And I have already shared the link to this Google Colab sheet, and the video will be also shared to all of you via email. And okay, then let's conclude our session today. Have a nice weekend. Bye bye.